Dear students, welcome to this chemistry module. This module course code is 21CYB101J. This is a 5 credit course, 3 credits for lecture, 2 credits for practical, and 1 credit for tutorial. So this is uh, the credit structure for this module. And first unit, majorly you will be studying coordination chemistry. So we will see what are the topics in coordination chemistry. This you have already studied in your grade 12, so you might know more about these topics. And myself, Arun Prakash, I am working as an assistant professor in research in the Department of Chemistry, SRM Chemistry. I am going to teach you this module for you. Now let's get into the topic, that is Unit 1, Coordination Chemistry. So like in our life, the coordination between the ligand and the metal ion determines the strength of that complex, and this is what about coordination chemistry is about. Let's see the topics one after the other. So coordination chemistry, it is the branch of chemistry that deals with the study of coordination complex. So in this unit, we will be mostly studying about different coordination complex, and mostly we will be studying about the coordination complexes with some specific geometry, especially tetrahedral and octahedral. So as you know that these coordination complexes have been known since the beginning of modern chemistry. They have been in the field for a long time, and early, there are coordination complexes which are well known, and they include dyes such as Prussian blue. You might have heard about this compound, Prussian blue, which is blue in color. So the early contributions to the field were from Swedish chemist Christian Wilhelm Blomstrand and Danish chemist Sophus Max Jorgensen. The most widely accepted version of the theory today was published by Alfred Werner. He won the Nobel Prize in Chemistry in 1933. So before you start the coordination chemistry, you should know the difference between a double salt and a coordination compound. Let's see what is a simple salt or double salt and what is a complex compound. Simple salt, as you know that a simple salt is formed by acid-base reaction. For instance, you take hydrochloric acid, react it with sodium hydroxide, and you will get sodium chloride and water. The sodium chloride is the simple salt, and this is the simple acid-base reaction. Double salt. So this is nothing but two simple salts are mixed together and which will form a double salt. So it is an addition compound in which simple salts don't lose their identity. And also it aqueous solution gives test to salt constituent ions. Double salts lose their identity in aqueous solution. For example, let's take potassium chloride and magnesium chloride. So alkali salt and alternate salt, and you are dissolving it in water, and it will form potassium chloride, magnesium chloride, and the hydrated form of these two salts, hexahydrate. And in aqueous solution, again, when you dissolve this double salt, they will not lose their identity. For instance, the potassium chloride will dissociate into potassium ion and magnesium ion and chloride ion. So the number of ions will be almost 5, like 3 chloride, 1 potassium, and 1 magnesium. And when you add silver nitrate to the solution, it will precipitate the silver chloride, because chloride ions, as you know, will react with silver nitrate and it will form silver chloride. And this is how a double salt will dissolve and it will dissociate in water. And now let's move on to the complex compound. This is something like the complex identity. Let's see how it looks like and what are its properties. Any aqueous solution that does not give test to its all constituent ions. For example, in the previous case, we have seen potassium, magnesium chloride. You can individually do the chloride test, magnesium ion test, potassium ion test. Whereas in the case, look at this complex compound, that is potassium percyanide. So K4FeCN6. So when you dissolve this in an aqueous solution, it will dissociate into potassium ion 4K plus. Thus outside the bracket you can say K4, so it forms 4K plus. And also this will form FeCN6 4 minus. so that it does not ionize to give individual ions inside the bracket, that is the complex. It will not form a P2 plus ion, and it will not give any test to Fe2 plus or Cn minus ions, which means that it will not ionize into its individual ions. Okay, so before you study the coordination chemistry, you should know some terminologies in coordination chemistry. Some important terms in coordination compounds, we will look into that. Coordination entity. So this is the first term you should know about. And this is nothing but it constitutes the central metal atom or ion. So metal atom can be any transition metal atom or ion. So which is bound or bonded to a fixed number of ions or molecules. That number of ions or molecules that bonded with that particular metal atom determines the geometry. For instance, if four ions are bounded with the metal atom, then it is, as you know, the coordination number will be 4. So the geometry will be tetrahedral. Similarly, when 6 atoms or ions are bounded with the central metal atom, then it will, coordination number will be 6 and the geometry will be octahedral, as you know. Let's take this example, CO, Cl3, NH3, rice. So this is a ammonium complex, and the number of ions attached with the metal ion is 3 amine ligands and then 1 Cl. So this Cl or NH3 is called ligand or ligand, you can call it. Why? Because they are rich in electron, whereas the metal ion is electron deficient in the d orbital. So this metal ions will accept the electron from the ligand. So this is called, this whole species inside the square bracket is called coordination entity. So here the cobalt ion is surrounded by 3 ammonium molecule and 3 chloride ion. There are also other examples for coordination entity like nickel, cobalt, carbonyl 1, tetracarbonyl 1, and also diamine, dichloroplatinum complex, and the well-known hexacyano ferrate complex, and also hexamino cobaltate complex. So these are the some examples for coordination entity. Now, let's see what is a central atom or ion. So this central atom or ion will be present in a coordination entity, which means a square bracket in uh, in our representation in a 2D plane, like in a whiteboard when you write. So the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement. So based on the number of atoms or ions that are arranged around the metal ion will give rise to its geometry or geometrical arrangement. So this specific central metal ion present at the center is called central atom or ion. For example, let's take this complex, the tetra-aquo and dichloronickelate complex. So in this one, so the nickel will be present in the middle, and the chloride ion, two chloride ions will be present surrounding this nickel, and also the water will be present around surrounding the nickel. So these 6 ions are ligands, and nickel is the central metal ion. And also we have the other complexes like penta amino chlorocobaltate complex and hexacyanoferrate complex. So here in this case, the first one, the metal ion has a positive charge, that is divalent charge Ni2 plus, whereas in the second case the cobalt is in 3 plus oxidation state, and the third one iron is in 3 plus oxidation state. In other words, you can call it central atoms or ions as Lewis acids, which are electron deficient, whereas ligands are Lewis bases, which are rich in electrons. Let's see, the ligands or the ions or molecule bound to the central metal atom in the entity. For example, it can be a neutral ligand like water or ammonia, like a simple molecules. Or also we have the larger molecules, and ethylene diamine kind of bidentate macromolecules are also possible, which tend to bind or bound to the central metal ion. Okay, classification of a complex compound. So look at this complex. This is a homoleptic complex. Same, which means homoleptic means same type of ligands. So you can see inside the bracket, you got four ligands and the copper. The orange one highlighted in orange is the central metal atom. You can also call it as CMA. And the blue one is the ligand. It is highlighted in blue for, uh, for our understanding. And also you have a counter ion, that is sulfate ion, outside the bracket. So you got the metal ion which is highlighted in orange, ligand in blue, and the counter ion without any highlighting outside the square bracket. And heteroleptic complex, this is also another type of complex where you will have more than one type of ligand. For instance, so here in the previous case you got four amino groups, right? When you are including one chloride ion, one chloride ligand, and when you form this complex instead of copper, platinum, then platinum will be your central metal ion, and four amino group plus one chloride will be your ligand, and sulfate will be your counter ion. Okay, so the two terminologies are over, and let's move on to the third one, the coordination number. So this is very important. So this coordination number only determines the geometry of the coordination complex. So in a coordination complex, the metal ion will be present, that we know. It will be bound with the number of ligand or donor atoms. So ligands, you can also call it as donor atoms or Lewis bases. Whereas central metal ion, we can call it as Lewis S. So the coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal ion is directly bounded. Just the number. How many ligands are bound with the central metal ion? That is your coordination number. For instance, look at this complex. This is a complex ion, PtCl6 2 minus. So how many ligands are present here? Cl6. So which means 6 Cl ions are bound with this platinum. So the coordination number of this complex will be 6. And similarly, this is an example for an octahedral complex, because 6 coordination number means octahedral. It will form the geometry octahedral. And instead of platinum, if you have nickel, and instead of chlorine, if you have chloride, if you have the amine ligand NH3 for amino ligand, so then tetraamino nickelate 2 plus charge. This one you can see that 4 amino groups are attached with the nickel central metal atom. So the coordination number will be 4 and the geometry will be tetrahedral. Similarly, look at the other, let's take another example, the complex ion, FeC2O43. So do you know what is C2O4? This is an oxalate ligand. So you have 3 oxalate ligand attached with the metal ion. So the coordination number will be 3. And similarly, COEN3. So En means ethylene diamine, a bidentate ligand. So the coordination number of both iron and cobalt is 6. Whereas why? Because C2O4 2 minus and En are bidentate. This is something important. For example, if you look at this complex FeC2O43, you will straight away say the coordination number is 3, but it is a bidentate ligand, so you have to count it as 6 and not 3. Similarly, ethylene diamine is a bidentate ligand, so your coordination number will be 6 and not 3. So this difference you should know. Okay, let's move on to the coordination sphere. So coordination sphere. So in the coordination sphere, what are the species present? So you will have your central atom or ion, and the ligands are attached to it, which will be enclosed in a square bracket, and it will be collectively termed as coordination sphere. So the coordination sphere is non-ionizable, and the ionizable groups are called as counter ions, which are present outside the bracket, and they are called as counter ions. For instance, in the complex K4FeCN6, so your coordination sphere will be the one with containing the square bracket containing FeCN and 6. So since the coordination number is 6, the geometry of this complex will be octahedral. And this K4 is a non-ionizable species, and therefore when you dissolve this complex in water, it will form 4 potassium ions and FeCN6 4 minus. The coordination sphere is, the charge of this coordination sphere is FeCN6 4 minus. As you know that Cyanide is a negative ligand. So for 6 cyanide, you get 6 minus. And if you want to calculate this one, the charge of this ion will be Fe2 plus. So the total charge 2 plus 6 minus. What will be the charge of this complex? It will be 4 minus. That is why you are putting K4. And the counter ion in this case is potassium ion K plus. Okay, coordination polyhedron. So this is something related to the spatial arrangement of the ligand atoms, which are directly attached to the central metal atom or ion. For example, if you have this hexa amino cobaltate complex, as I said, the 6 amino group will be spatially arranged like 4 in the plane and fifth one will be above the plane. For example, you put the cobalt atom on the, for instance, let's take this white paper. If the red dot here is the cobalt ion, so that 4 atoms, that is amine ligands, you can put in this plane, and then the fifth amine you can put above the plane and the sixth one below the plane. So when you connect this point, you will get an octahedral complex. Similarly, tetracarbonyl nickelate and tetrachloroplatinate. Here the, what is the coordination number of this complex? 4, right? They are not bidentate ligands, so it will be 4. So nickel cobaltate and platinum tetrachloroplatinate. Since the coordination number is 4, obviously your geometry will be square planar. Classification of ligands. Let's move on to the classification of ligands. Monodentate ligand. So the first one is monodentate ligands. If the ligand have only one donor atom, that means it can only donate one electron pair. So you should remember the ligand is the one which will donate one electron pair, not single electron. So it will donate one electron pair to the central medical atom, or known as monodentate ligand. So the example, best example would be, before seeing the example, let's see the classification. Monodentate ligands can be further classified into 3 types. So how we can classify that? Based on their charge. For instance, aqua is the ligand water, and NH3 is the amine ligand, and CO is the carbonyl ligand, and CS is the thiocarbonyl, and NO is the nitrosyl. So these 5 ligands are example for neutral ligands. And let's see the other one. What would be the other examples, the other types then? Cationic and anionic, which means the ligand is having a positive charge, that is cationic. If it is having a negative charge, that is called anionic. So oxygen with 2 plus charge, that is oxygenium. Nitroso group with the plus charge, that is nitrosilium. So these are 2 examples for cationic ligands. And let's see the example for anionic ligands, halogens, like fluorine, fluoride, bromide, iodide. So fluoride, chloride, bromide, iodide. You can also call fluoro, chloro, bromo, and iodo. The ligand name we should say fluorido, chloride, bromido, and iodide. And also the best known example is hydroxide, hydroxo or hydroxide, and nitro is NO2 minus. So look at this, all these ligands are having negative charge, so they are called as anionic ligands. And bidentate ligands. The best example is ethylene diamine. It is having 2 nitrogen atoms which are having lone pair, which can be donated to the metal ion. So since 2 nitrogen atoms can donate the electron, so which are indicated by the arrow. So what does this arrow mean? It is a coordinate covalent bond, which means the arrow point will be pointed toward the metal ion. What does that mean? Which means this amino group containing this lone pair electron is donating the electron, and since the metal ion is accepting, the arrow is headed toward the metal ion. So this is how the structure will look like. Simple one, you already know, CH2 double bond CH2, ethylene, right? So when this is a saturated compound, ethylene diamine, so single bond, instead of that, you will have NH2 amino group attached on both ends of the CH2. And as I said, oxalate is also here. Oxalic acid, you might hear about this now. So oxalate ion. So which means, look at this one, C double bond O, single bond O, minus, and similarly you will have C double bond O, single bond O minus. So these two oxygen atoms are having negative charge, which means that they are electron rich and they can donate the lone pair to the metal ion, and in this way the coordinate bond can be formed. Again, this arrow ray is headed towards the metal ion as it is accepting the electrons. Let's move on to the next one. And the other one is dentate, is which means like a teeth, like a crab is having a teeth kind of things, no? That is called dentate. And mono means one teeth, bi means two teeth, and these are two nitrogen atoms, and these are two oxygen atoms which are binding. And then ambidentate ligands. So these are the ligands which have two different donor atoms, but at a time of coordination, such a ligand can be coordinated by either of the two donor atoms. Let's see, like if you are having this metal ion, this can be coordinated either by carbon or nitrogen. For instance, if it is coordinated through carbon, it is called cyanido, and if it is coordinated through nitrogen, it is called isocyanido. So here you will have the triple bond between carbon and nitrogen. And also the best example would be nitrito and nitrito, uh, oxygen and nitrogen. So here you will have uh, the ON double bond O. So if the metal ion is coordinated with the oxygen atom, that is called nitrito O, and if it is coordinated with N, that is nitrito N. And this is like, looks like a chelate. The example is ethylene diamine, and exactly this looks like a T. These two NH2 groups. Okay, monodentate over bidentate and polydentate. Poly means four or more, right? So more than two, you can say that. So several donor atoms are present in a single ligand. The best example would be ethylene diamine tetrastic ion. So this you will also be studying in the practicals, hardness determination, water hardness determination. You will be using EDTA, and you will be chelating the rare earth, alkaline rare earth metals like calcium and magnesium present in the water, which are responsible for the hardness of water. I also would like to mention that this is a joint course, so the practical and theory will be linked. So that in the first part, first module, so whatever the theory you are learning, you will be applying in the practical, and particularly you will be learning about the alkalinity and hardness determination of water, like that, which the syllabus has been changed. So, okay, let's come back to this one. Polydentate ligand, BDTA metal complex. So metal is present at the middle, and you have these four uh, chelating groups. So that is CH2, CH2N, and you also have the tetra acetate ion. Na? So CH3COO minus is acetate. So with this N, this CH2COO is present. So what does this dotted line and this thick line mean? So this means this is a wedge-shaped bond. These groups are pointing towards the viewer and away from the viewer. So that is how they are. Why we stereochemistry, you will learn more about this one. But look at this one. This is the simple structure of ethylene diamine. Exactly, you know that ethylene diamine means CH2, CH2, NH2, NH2, right? So instead of NH2, you will have these two acetate groups at the one side of the NH2. For example, in the right side, instead of two hydrogen, you will have CH3COO, CH2COO, and CH2COO. Similarly, here with the nitrogen, you will have CH2COO, CH2COO. Okay, so several atoms, 6 hexadentate ligands are there, and I have numbered this one so that you can understand how we already seen nitrogen and oxygen are donor atoms, right? So yeah, from the acetate part, oxygen will be donating, and from the nitrogen terminal, nitrogen group will be donating. Okay, so whenever you discuss about the coordination theory, coordination chemistry, there are two famous theories. One is Werner's theory, and also we will talk about the crystal field theory. Let's see what is Werner's theory. Werner postulated that Metal ions have two different kinds of valency. What are they? Primary valency and secondary valency. Primary valency is related to oxidation state of the metal ion. So we have seen many complex, right? For example, FeCN6 4 minus, K4Fe CN6 4 minus. What is the oxidation state of that metal ion? 2 plus. So in that case, the primary valency will be 2 plus. And what would be the secondary valency in that case? 6 cyanides are linked with the Fe2 plus ion in the FeCN6 4 minus complex, hexasign of ferrate complex. So that the coordination number will be 6. So the secondary valency will be 6. So remember, primary valency means oxidation state, secondary valency means coordination number. Very straightforward explanation. And most common coordination number will be 6 and 4, and the less common will be 2, 5 and 8. It is nothing but number of bonds formed between the metal ion and the ligands in the complex ion. Okay, so ligands, we already seen the explanation and definitions. The molecules are ions coordinating to the metal or ligands. So I don't want to repeat the same thing. And they are usually anions or polar molecules, different types we have seen, and they tend to interact with the metal ions. Like if when you say water, so you in the on the oxygen atom you will have the lone pair of electrons which will be donated to the metal ion. Similarly, nitrogen will have one lone pair which will be donated to the metal ion, and chloride ion and cyanide also will be having the lone pair electrons. So this is how a coordination complex of cobalt has been formed. Okay. So for the geometry of the coordination complex, I will give separate notes like ML2 to ML6, which will be easy to follow, and each and every geometry I would like to cover in that specific notes, and you can also refer to the class notes for the geometry of coordination complex. We will see what are the geometry, etc. But before that, I would like to move on to the next important theory, which is crystal field theory. So crystal field theory is very important in determining the geometry of the complexes. There are certain limitations which we will discuss at the end of this lecture. This theory is based on the concept when negative charges of the incoming ligands on the negative end of the dipolar molecules like amino or water attract the positively charged metal ion. There will be a repulsion between the d electrons present on the metal ion and the ligand. So this theory is based on the repulsion of the electronic cloud between the metal ion and the ligands, which will, so when they are repelling, what will happen? Obviously they will be pushed apart. That will lead to the change in the geometry of the complex. You will see one after the other. So to understand the crystal field theory, CFT, we should have some certain assumptions when dealing with CFT. So the ligands are treated as the point charges. It can be negative, positive, or neutral. We already seen the types. So the interaction between the metal ion and the ligand are treated purely electrostatic, because opposite charges leads to electrostatic interaction, mostly ionic interaction. No covalent interactions are considered, which means no chemical bonding, direct chemical bonding happens. And also covalent nature is considered in ligand field theory and molecular orbital theory, and not in the crystal field theory. So in this case, we have to, according to CFT, we have to assume that metal ion is an isolated gaseous ion. And so for example, if you are having a transition metal ion or it will have d orbitals that we all, d block elements or transition metal will have the d orbital that we know. So d orbitals means 5 orbitals, that also you know. S orbital means 1, p orbital 3, d orbital 5, f orbital 7. So we are going to study, mostly we will be studying about d orbitals in this module 1. So 5 d orbitals are degenerate. What does the term degenerate means? It is equal energy. All the d orbitals are of same energy. So when the metal ion d orbitals is present, all the orbitals are of same energy. But whereas when the ligand is approaching the metal ion, Due to this electrostatic interaction or electrostatic repulsion, the metal ion orbital will be either pushed up in energy or down in energy. That leads to splitting of the orbital. That is called crystal field splitting. Okay. So let's see, when a hypothetical spherical field of ligand approaches the metal ion, that is the ligands are approaching, d orbital still remains degenerate, but note that their energy level is raised a bit. Why? Due to the repulsion between the orbitals of metal and the ligand. That particular energy level, the same energy level, that is called barycenter. So the orbital metal ion, orbital d orbital energy will be pushed either above the barycenter or below the barycenter. The most common geometry of tetrahedral transition metal complexes are octahedral, tetrahedral, or square planar. So the field provided by the ligands is not at all symmetrical. So the d orbitals are unequally affected by the ligand field, and the degeneracy of the d orbital in that particular metal is removed, and it is split into T2G and EG. We will see one after the other. So how orbitals will be affected when ligands approach a metal in an octahedral arrangement? So look at this one. This is an octahedral complex. Dear students, we will continue this lecture. We will see how the orbitals will be affected when ligands approach a metal in an octahedral arrangement. We'll see one after the other. So in the picture on your left, so these are orbital lobes which are represented by different colors like metallic gray, yellow, and uh, deep red. So as you know that ligands with their pair of electrons approach to the metal atom in all three directions or along the all three axes like x, y, and z axis to form an octahedral complex. So now this particular energy point that is at the center is called barycenter. As I told you before, when the ligands are approaching the metal ion in all three axes x, y, and z. So we know that the orbitals are containing electrons which are negatively charged. So the negative charge of the electrons present in the metal ion orbital and the ligand orbital will repel each other. Due to this repulsion, the energy of the metal ion orbital will be pushed down or up. So these are the two possibilities. So when they are pushed up, so the possibility is in this case, those ligands approaching in the Z and Z axis, as well as, what do you mean by x square and y square? Which means that the ligand orbitals are present between x and y axis or pushed up. So these two orbital energies are pushed up. So what is the other possibility? So these d orbitals are having lobes pointing directly at x, y, and z axis as represented in yellow color, are repelled most by the electron repulsion. So the other possibility is dxy, dyz, and dxz. These are the three orbitals whose energy levels are pushed down, and as a result, their energy is lowered. So these d orbitals are not pointing directly, and they are represented by the this brown color. Okay, maroon or brown. Okay, how the splitting of d orbital occurs. So this pictorial representation gives you an idea how the orbitals are split. So let's take an example, 3D orbital. As you know that these pi orbitals will be present. One is dx, dyz, dxz, dxy. You can also arrange the other way, dxy, yz, xz, it's fine. And then, so which means they are oriented in the uh, between the axis, means we have seen dx square. So there are two possibilities. One is between the axis and along the axis. So when it is along the axis, you can call it as dx square minus y square, dz square. Between the axis means, for example, dxy. What does it mean? So the orbital is oriented between x and y axis. Similarly, here dxz, so it is oriented between x and z axis. Dyz means between y and z axis. That's simple. Okay, so the two sets of orbitals are formed after splitting. Why? Due to the when the ligand orbitals are approaching the metal ion, there is an electrostatic repulsion between the electronic cloud in the metal ion orbital and the ligand orbital. This we should be clear with this one. Only purely electrostatic repulsion. Okay, so these three orbitals energy are lower. The first three, d yz, dxz, and dxy. So what are the other two orbitals whose energies are pushed up? So these are the two orbitals which are oriented along the axis. So they, that is dx square minus y square, which means the orbitals are oriented in x and y axis. Dz square means the vertical axis. So that is also pushed up. So the difference in the energy now between T2G and EG is called delta G, crystal field splitting energy. So T2G, these three orbitals whose energy are lowered are called T2G, and those two orbitals whose energy is raised is called EG. The energy difference between T2G and EG orbital constitute the delta G. These five d orbitals are degenerate. Before splitting, they are all having similar energy, but after splitting, their energy difference occurs. So this is called crystal field splitting energy. Here G means gerade or German for even. EG means doubly degenerate. And here three orbitals. So T to G means triply degenerate. EG means doubly degenerate. T to G means triply degenerate. EG means exemplary gratia in vacuum. Okay, so in your exam point of view and also in your like CT's class test one, mostly this crystal field theory is very important, and you have to draw a diagram how you will represent the crystal field splitting. So you can draw this diagram, which is very important. So just put an axis, an arrow pointing upward, and mark it as energy, and put 5 lines. 5 lines means it represents 5d orbitals. So this you can label it as isolated metal ion orbital, and you have to specify all d orbitals are degenerate, which means same energy. So then you put a slanting line again until the ligand approaches, all the electrons will be degenerate, but the average energy of the metal ion in the spherical field you are putting, again they are all are degenerate. And this particular dotted line, the central point, is called barycenter. I already told you. So above and below, above the barycenter means energy is raised, and below the low barycenter means energy is lowered. So now you got two sets of orbital, that is T2G and EG. T2G is formed by three orbitals dxy, yz, dzx or xz, and EG is constituted by dx square minus y square and dz square. So this particular energy gap between EG and T2G is called crystal field splitting energy. It is generally denoted by delta O. So delta O or delta octahedral. So you can represent by OCT or 10 dq. The total energy value for this is 10 dq, where here delta represent the crystal field splitting energy and O represent the octahedral. So when you are representing tetrahedral, you can put delta T. So that O or T symbolizes whether that complex is octahedral or tetrahedral. Since the overall energy is maintained, so the energy of the three orbitals are stabilized or lowered, and the value is 4 dq. Out of 10, it is 4 dq. If you consider it as 1, then it will be 0.4. Am I right? So minus 0.4, and the energy will be raised by, if it is 10, then it is 6 dq. Whereas delta O means, if you consider it as 1, then it will be out of 1, 0.6 plus 0.6. So this magnitude is also important. So all these energy assignments are based with respect to the hypothetical energy field or barycenter. So the difference between the Eg and E is called the crystal field splitting energy, and this is often expressed in the energy parameter called the 10 dk. Okay, so this is also a pictorial representation, and then to try to understand this concept, how the ligands are approaching metal ion. So a 3D view. So this all you know, this geometry is a cube, and then the cube's planes are represented by, edges are represented by the dotted lines, and you have a two square which are connected to form a cube. And in that you have two faces, right? This is the front face and this is the back face. So imagine four ligands are lying at alternating corners of a cube. For instance, this is your cube now, the front face. So alternating corner here, here not present. So here not present. So alternating corner. Similarly, the back face now. So you can put alternating corner. Here it's not present. Here it is present. Not present. Here it is present. So out of four corners, you will get two ligands at the two corners. Just remember as simple it is. Okay. And then you got this dx square minus y square and dz square orbital on the metal ion at the center of the cube, lie between the ligand, and this particular dxy and dyz and this dy. What is that? It is T2G. Am I right? Triply degenerate, point towards the ligands. So as a result, this splitting will occur. We will see how it occurs. As I told, you will get x square, z square, x square minus y square. Whereas here it oppositely happening. Just remember, this is the only difference between tetrahedral and octahedral complex. Okay, so octahedral complex we already seen, but tetrahedral complex only those between the axis. For example, look at here between x and y, and it is here it is present between y and z, right? So these here the ligand orbitals are approaching. As a result, only those atoms or the ligands present in between the axis will be pushed up. Okay, so what are the orbitals present in the octahedral? That is three orbitals. T2G are present now. Here T2G is present up, moved up. Look at here, dxy in between x and z axis, yz and xy are pushed up. So the orbital oriented along the axis, that is dx square minus y square and dz square are lowered in energy. As a result, you will get 0.6 delta T. Remember that letter T. O means octahedral, and then 0.4 delta T. So you will get delta T is equal to 4 by 9 delta Q. This is an important relationship, which means that compared to the octahedral splitting energy, delta tetrahedral splitting energy will be relatively half. You can say like that, 4 by 9. So this is how this relationship is very important in the even in the multiple choice. They have asked many times. Delta T is equal to 4 by 9 delta O. Why it happens so? Remember, in octahedral complex there are 6 ligands. In tetrahedral complex fewer ligands are there. How many? 4 ligands. So compared to 6, 4 is less in number now. So obviously less ligand, less electrostatic repulsive force, and as a result the splitting energy will be half of the octahedral splitting energy. Just remember that. And then this picture gives you, and suppose if they are asking, can you compare the crystal field splitting diagram of a tetrahedral and octahedral? So if they are asking you in the exam only octahedral splitting energy diagram, draw the first one. And when they are asking the tetrahedral, draw the second one. Remember, the energy should be half. Look at here, when they are asking you to compare, then you can draw this diagram where both crystal field splitting energy diagram of octahedra on the left and tetrahedral on the right have been shown. So look at here, dxy, dxz, dyz. This is T2G. But whereas in tetrahedra, this will be up. So dxy, dxz, dyz, T2G. And then Eg will be at the top in the case of octahedra. The energy difference we already seen now. Either you can say 0.6 delta O minus 0.4 delta O, or in terms of this also, you can this fraction also, coordinates also, you can do 3 by 5 delta O, 2 by 5 delta O. Similarly, this energy will be opposite. So 0 0.4 delta O will be on top and 0 0.6 delta O will be on at the bottom. 2 by 5 will be at the bottom for octahedral, 2 by 5 delta T will be present at the top for uh, tetrahedral. So you practice this diagram. As many times you are practicing, you can make it perfect. And also this relationship. So don't forget to put the mark the energy on the left with the arrow pointing upward. So this mostly they will ask in 5-mark questions or maybe in 8 marks also. Sometimes they have asked as one of the options will be this crystal field. Both in the main exam and also in the CT is a very important question. So I would like to highlight that one. So pay attention to this one, this crystal field splitting diagram. Okay, so the optical properties. Let's move on to the optical properties. I will quickly go through this property. So, like as you know that the octahedral complex have different colors. As you know, potassium ferricyanide. Many of you might have seen ferro, very different colors, yellow and orange. Similarly, this hexa arco titanate complex has a deep violet color. So why does this happen? So this all you should know that these transition complexes, these transition complex coordination complexes are giving color due to the dB transition between T2G and EG. The electrons will be transition will be happening, and due to that transition, the complex will be colored. So depending on the absorption wavelength. So for this complex, you can see that this is the UV visible absorption spectrum. So as you know that either you can represent in wave number, wavelength, right? Wave 1 by lambda is the wave number, na, mu bar. So here we have represented like this. So these are the wave number, and here this complex solution is giving a absorption maximum. So here, since it is represented in wave number, so mu bar max, that is 20,300. And when you convert this into energy, so the simple conversion will be 1 kilojoule per mole will be equivalent to 83.7 centimeter inverse. So now this absorption maximum is in wave number, right? So you have to to convert this into kilojoule per mole, you have to divide this number with the 83.7 centimeter inverse. Then you will get the 243 kilojoule per mole. This way you can calculate the octahedral. Why? The 6 Lagan 6 coordination number. So this is an octahedral complex. So you can calculate the octahedral splitting energy, which is 243 kilojoule per mole. The energy diagram is also given here. It is a D1 system, Ta3 plus. So one electron will be present in T2G. Once it observes the light, this electron in the T2G uh, will be jumped to the EG transition will happen. So this is also a high spin complex because one electron is present, so it can easily move to the, since the the delta O energy difference, splitting crystal field splitting energy difference is very small gap, so the electron from T2G can be easily jumped to the EG level. Due to this DD transition, this emits violet color. Okay, so D1 D10 transition also will learn. Okay, now if you you will get a numeric, like they will give a wavelength, and they will ask you, okay, this complex observes at this particular wavelength, and what would be the color of that complex? They will be asking like this. For that, you should know about the complementary color wheel concept. Let's see what is complementary color wheel and how you can draw this complementary color wheel. First, draw a circle. Just draw a circle in your notebook, and then put a slanting line like X. Okay. Basically, I have split this circle into how many quadrants? 4 quadrants I have split. And then draw a vertical line. So now how many you have got? 1, 2, 3 on the left, and sorry, 1, 2, 3 on the left. Yes, 4, 5, and 6. 2 extra coordinate. We have quadrants. We have got 6 quadrants are present, and then you just put a horizontal line. So now you will get 8 quadrants, and then just put B, I, B, G. So what is that? Visual. Violet, indigo, blue, green, yellow, orange, and red. So this is how you form your color wheel. And now, if you have this violet at 400 nanometer, and then just label it as 420, 450 nanometer, 490, and then 560, 600 nanometer, and 650, and then finally 800 nanometer. So this is the UV visible absorption range. So we have marked all the wavelength. And then remember this conversion, x nanometers equal to, so like 1 lakh, right? 10 lakhs by x centimeter inverse. So this number, um, you just for conversion you have to remember, when you divide this by x, then you will get centimeter inverse. When it is given in centimeter inverse, then you have to divide this with nanometer to convert it to this is like wavelength to wave number conversion. So we have to follow this conversion. And then 12,500 already I showed you, and then 25,000. So the complementary color, for example, a complex observes at the violet means if it is observing between 400, if a complex observes at a wave number of 25,000 centimeter, if you apply this one, so all you know this, that you know the wave number now, then just apply in this equation, and then you will get the wavelength. So that will be 400 nanometer. That corresponds to, what is the complementary color of violet? Yellow. So obviously this complex will emit yellow color. So this is how the numeric will be problems related to color determination. When you are thorough with that color wheel diagram and conversion factor, wave number to wavelength, then that's simple. You can calculate your determine the color of that complex. So what would be the problem look like? Calculate the wavelength of light having wave number 24,000. Already we have seen that the wavelength would be 400 nanometer, and the energy also they are giving 239 kilojoule per mole, and 1 kilojoule per mole 83.6, and you can divide that to get the wavelength also. And this is simple one, like Planck's constant, E is equal to h mu, h is the Planck's constant, whereas E, you know, hc by lambda. C is the speed of the light. When you substitute this one, mu bar is nothing but 1 by lambda. That's why I told, when they are giving wave number 24,000 centimeter inverse, that is nothing but mu bar. What would you do to get the wavelength? Just move the lambda to the left side and bring the wave number, that is 24,000 centimeter inverse, to the bottom. So you will get 1 by 24,000 centimeter inverse, that will be 400 nanometer. Okay, like that you can do. Okay, this is also an important one. What are the factors affecting the magnitude of delta, that is crystal field splitting energy? So you have to remember that higher oxidation state of the metal atom corresponds to larger delta. What does it mean? If a complex is having 2 and 3 oxidation states, same metal ion. Look at this example, cobalt. Here also cobalt, ligand is same, hexa amine complex, amine ligand, and it is a 6 coordination number, the complex. So it will be octahedral. These are all we learned now. So, but look at this oxidation number. What is the oxidation number of cobalt? 2 plus 2, and here plus 3. So according to this one, the important factor is oxidation state. So which complex is having the higher oxidation state? The one on the right. So look at the number, the delta value 22,870 centimeter. Obviously, this is half of that. Look at that. Even one oxidation state can lower the delta value by half. Just remember that one. So here Fe2 and Fe3, it is also an octahedral complex. Here there is also a difference in the delta value, and obviously the complex with the higher oxidation state, that is plus 3 oxidation state, ion in plus 3 oxidation state, is having 35,000 wave number delta value, whereas it is the other one plus 2 oxidation state is having only 32,200 centimeter inverse. So group heavier analogs have larger delta. And then for hexamine complex, let's take example. So these are hexane complex, and in this one, cobalt, rhodium, iridium. So the heavier analog will have the delta. For example, compared to cobalt, rhodium and iridium are having higher mass number. As a result, they are having delta, higher delta. And the third one is geometry of the metal coordination unit also affect the delta greatly. For example, tetrahedral complex ML4 has smaller value than the octahedral. Why? Obviously, more ligands, more splitting, or more electrostatic repulsion. Okay. Uh, for example, same metal ion cobalt, oxidation state is same, but the coordination number is different. 4 and 6. So the geometry will be different now. 4 means tetrahedral, 6 means octahedral. So octahedral is having more higher splitting energy, and ligands can be arranged. So this is one of the important question, spectrochemical series. What is spectrochemical series and how they are arranged? So ligands can be arranged in a spectrochemical series according to their ability to increase the delta at a given metal center. Mostly the halogens are weak, so they are present at the left corner of this spectrochemical series, and also like cyanide and CO, the stronger ones are present at the right side, and the neutral ones like water, amine are present at the middle. As a result, you can see that for the L6, especially the aqua one, and also for this one, fluoride one. So the fluoride one is having lower delta value compared to the aqua one. Why? Because fluoride is the weak ligand, whereas aqua is the strong ligand. So strong ligands will give higher splitting energy. Similarly, here fluoride is giving lower, and water is aqua is giving higher. Similarly, the NH3 will be giving higher, and cyanide will be giving higher as well. So the uh, so this is how this example will be here. Also the same. So the order of delta along the group follow this order: 5D, 4D, 3D. So this is I already told you about the heavier analogs: 3D, 4D, 5D. Obviously, 5D will be giving higher energy, and in this case, delta O, delta P. Weak ligand and electrostatic field produced by different. Dear students, welcome back to the lecture. In this follow-up lecture, I would like to discuss about the spectrochemical series. So this is one of the important topic in coordination chemistry. So this spectrochemical series has been arranged based on the strength of the ligand interaction. So as you know that the strength could be stronger, weak, or moderate. So the ligands are arranged in a sequential order with the increasing order of their field strength or interaction, which means that weak ligands will be placed at the leftmost corner. Let's look at some of the known ligands like iodide, bromide, uh, thiocyanate, SCN minus, sulfur bonded, chloride, fluoride. Mostly the halogen types are weak ligands, and they are placed at the left topmost corner. And look at the ligands position in the top right. You can see that nitro, triphenyl phosphine, and specifically cyanide and carbonate are strong ligands. And also you have the hydroxide in the middle, position in the middle, and aqua and NCS, nitrogen bonded, and also water. So these are in between strong and weak ligands. So here I have shown some of the ligands which are considered as weak field and which are considered as strong field. Water, fluoride, chloride, and hydroxide are example for weak fields ligands. And strong field ligands, you have the carbonyl, cyanide, amine, and triphenyl phosphate. Let's look at this energy diagram. So energy coordinate on the left, where the increasing energy level has been shown by an arrow pointing upward. And the There is an arrow, horizontal arrow, which means that the crystal field splitting energy delta is increasing from left to right. And you have the T2G below this arrow and EG above the arrow. T2G, as you know, 3 orbitals, and EG 2 orbitals above. So when you move from left to right, you can see both the T2G energy level is lowered. That's what we learned in crystal field theory. And EG orbital energy is increasing from left to right. And let's take an example of chromium based complexes. So chromium is a D3 system, and we take 4 examples. One is having all 4. Look at the coordination number of these 4 complexes. The coordination number is 6. No? So it is an all are octahedral complex. Fluoride. So F minus fluoride is a weak field ligand, and water. So which means it is also a weak field ligand, and you have the amine, which is a strong field ligand, and cyanide, which is a strong field ligand. So compared to fluoride, look at fluoride here, it is positioned here, and water is next to fluoride. So which means water is aqua ligand is stronger than fluoride. So based on this spectroelectrochemical series, you can see since it is a D3 system, all 3 electrons will be occupying the T2G. There is no fourth electron, so it is very straightforward. And as the strength of the ligand from fluoride to cyanide is increasing, T2G orbital energies are lowered and EG level orbital will be increasing as well. So this is how the spectroelectrochemical series is arranged. And now let's move on to, so you see all 3 are D3 system.